Okay, so let me go to the whiteboard, right? Okay, so bootstrapping, how does it work? So the algorithm is actually quite simple, right? Okay, so basically, suppose you have some observations, right? Suppose x1, x2, xn. Okay, so this is a, a vector of observations, right? And then suppose you want to find out something, like for example, you want to find out some parameters like the median of the population, or you want to find out the coefficient of variation, which is basically sigma over mu, right? Things like this, right? So classical inference either does not have any solution for these problems, or the solution is very cumbersome, so that it cannot be routinely applied. But let's see how bootstrapping solves the inference problem using a very simple algorithm. Okay, so suppose we want to find out the median parameter, right? So let's say we write mu with a tilde. Okay. Suppose we're interested in this. Okay. All right. So what do we do? So the first step is we resample the observation vector x n times, right? So it depends on how many observations are there, right? There are n observations. So we resample x n times. Resample x n times with replacement, right? So when you make a replacement, so you will creates a pseudo sample, which we will denote as x, maybe 1, okay? Or in general, you may just denote it with I, right? And then step 2. So this pseudo sample can be something like this. For example, x4, x2, x1, x4, and so on. Okay, x5. So still n of them. Okay. Okay, then step 2 is you compute the statistic of interest using the pseudo sample, right? And over here, there are several possibilities. One possibility is as follows. One possibility is you could compute, for example, if you're interested in the sample the population median, you could compute the sample median, right? Okay. All right. So, and then you could okay, we'll just compute the sample median for this example, right? Okay, so it's just sample median for this example. So this one we would write it as a t of x I, okay? And then basically your step 3 is to repeat step 1 and 2 b times, right? Where your b is generally 10,000 times should be enough, right? So in this case, so how do you make the inference, right? Now, first thing is the standard error of your sample median, which you cannot find using any formula except for the asymptotic case, which we'll look at that later, is approximately equal to the standard deviation of the bootstrap distribution of Txi. Okay. So basically, this is your I is 1, 2 until B, right? Okay. So basically, when you repeat step 1 and 2 up to 10,000 times, you will get 10,000 values, right? With different pseudo samples, okay? And this will form some kind of a distribution, right? Okay, will form some kind of distribution, and then the standard deviation of this distribution is equal to the sample, the standard error of the statistic that you want to find out. Then the second thing about this is that the you could actually take the if you want to find out the 95% confidence interval for the population median, this is equal to approximately equal to the 2.5 percentile, the 2.5 percentile of the bootstrap distribution to 97.5 percentile of the bootstrap distribution, okay? Which basically means that over here, this is your bootstrap distribution, right? So basically you'll find the two values here. This is the 2.5 percentile. This is a 97.5 percentile. You'll find these two values such that the middle part here is about 95%, right, of the total. Okay, so this will allow you to construct the 95% confidence interval or any kind of percentage, right? Generally, we just use 95%, right, for usual inference problems. Okay, although of course theoretically you could calculate any sort of confidence interval, but for applied work, generally people just stick to 95. Okay. All right, so it's a very simple algorithm, and that's why it is in wide use now, because it is simple and powerful. So it's easy to implement. That explains why it is something worth learning. If it is too complicated, then no one bothers to learn about it, right? Except the academics. Other people who are doing just applied work will not be able to handle the complications, right? So let's look at some examples. And look at the example in the lecture notes. Let me go to that. So this example, let's go to example 5.21. Okay, so you have read about that, right? This is the an example of trying to convince you that bootstrapping actually returns the standard deviation that you get from the bootstrap distribution is actually almost the same as the SE from that you obtain from theory, all right? When the theory can be applied. So first example here, it says the data comes from an exponential distribution with mean 1, right? So this is skewed data. For sufficiently large sample size, say n equals to 200, the SE of the sample mean is approximately sample standard deviation over square root of n. right? So for the distribution of the sample mean, you could appeal to the central limit theorem, right? So your 95% confidence interval is basically just x bar plus minus 1.96 sample standard deviation over square root of n, all right? Because your n is sufficiently large. If you want to find out the 95% confidence interval for the sample median, then of course you could also appeal to, let me see, this meeting will end in 10 minutes. Huh? Why 10 minutes? Okay, never mind, I'll handle that. I already purchased it. Okay. Okay, so let me see. All right, so you go to this part here. So I want to check if you use the Sheffer-Maritz formula for the standard error of the sample median, that's about 1/2 square root of n times exponential minus the sample median, right? So let's check, right? So let's look at the R code. Okay. So here the R code, basically you it's annoying. Okay, much better now. All right. So basically you set your sample size. Okay. Is the resolution clear? Let me see. Doesn't seem to be. Single page. How's the resolution? It doesn't look that great on my, I'm using my handphone to act as a mirror. It doesn't look that great. How about everyone? It's fine? All right. Okay, so here, basically this is simulation. I think by now you should be able to understand the this R code quite easily. Okay, so here you basically have, this is from a theory, right? Okay, this is a particular set SIT3003 so that you will get the same answer, right? Then this is the bootstrap, okay? So over here, this whole thing here is the function to do the one step. This is to do step, your step 1 and step 2, all right? Okay, you basically sample with replacement, right? Sample the data. DAT is the input, right? Which is your data vector. You sample how long equal to the length of the data, right? And you replace equals to true, right? So you sample with replacement. And then after that, in this problem, I want two statistics. One is the mean, one is the median, right? So I return these two values, right? So that's done. That's very easy. And then a bootstrap distribution is basically I just iterate this 10,000 times, right? Operating on this bootstrap function, I operate it many times. Okay. Right. So basically, note here carefully that I'm bootstrapping X. Yeah. So I'm actually resampling X. This X is a particular realization, right? It's our data. So I'm resampling that with replacement. Okay. And then after that, this one is just, this T is just to transpose it so that if you don't do that, your mean and median of your pseudo sample are on the rows. So once I transpose it, they are on the columns, right? That's easier to read. So over here, if you apply the bootstrap distribution, so you iterate through this distribution here, right? So this is a distribution of the mean and the median of your pseudo samples. So I find the SD, right? So the SD will be about 0.0798 for the first one is the mean. The second one is 0.06 for the median, right? Okay. And this is SE mean and SE median are the standard errors that you'll find from the formula, okay? So from theory, right? So the first one for the sample mean is 0.08, for the sample median is 0.06, right? It's extremely close, okay? So this tells you that the bootstrapping actually works, okay? In fact, if you didn't know this result, you just use these results from a bootstrapping, it would have worked as well, right? You would have got something that's almost the same as from theory. And then for this part, this is on getting the confidence interval, right? So you basically do apply, and then you find the quantiles, right? The quantile function will give you, so you specify two values, one 0.025, the other 0.975, you'll get the 2 percentiles that you want. So for the first column, this is for the mean, okay? The second column is for the median, right? So, so that allows you to construct the approximate 95% confidence interval, okay? Now for the sample mean, you can check, right? You take the mean, subtract 1.96 times SD over square root of n, right? So you appeal to the central limit theorem. So you use that result is about 0.762. You use bootstrapping 0.768, very close. And the other one is a difference of 1.08 and 1.076, okay? So almost the same. So this part here, there's for the median, there's nothing to guide the formula, but you could trust the result from bootstrapping, okay? So this basically tells you one thing, that bootstrapping already solves the problem of estimating standard error. As long as you have your data, that's it. It will solve it case by case, right? So the algorithm is very general and it works magic, right? No, so that's why the person who invented this method received some prize for lifetime achievement in statistics. Okay, of course the theory he has proof and all those kind of formal mathematics, which convinces the practitioners that the methods actually work, right? And of course the key part for this method to work is that your data, all right, over here, this data here, right, which you got from your population, they must be sufficiently representative, right? They must actually cover the amount of variation, right? Capture the variation in the population. So that means there's only one way to get it, which is you have some random sampling. Okay, you have some randomization method to do it. Okay. Okay, so I need to do some. Okay, just a second. Let me manage. Okay, so having said that, we could also actually use bootstrapping for calculating p-values, right? Previously, we learned how to use the permutation test, right? Using permutation test to actually do to simulate the null distribution and then compute the p-value. It turns out that bootstrapping can also be used, okay? And in fact, it's much easier to use than permutation test in this case. Okay, so I'll give you an example here. This is an example of a t-test, right? Two-sample t-test. Now, when you use bootstrapping to do to calculate p-values, you have to do some kind of transformation onto your data. For example, if you do a two-population test and you do a t-test, right? You use bootstrapping to do your t-test. Okay. Now, there are some good reasons why sometimes you might want to also try to double check your t-test results with your bootstrapping t-test. One of the reasons is because when you use t-test, right, there's an inherent assumption that your data are normally distributed. Okay. Usually in the textbook, right, in first year, you might have recalled that when you use t-test, you're asked to do some kind of checking of normality, right? Check that the data are normal. And then once that is satisfied, then you proceed to do your t-test, right? And if the data are not normal, then you do some kind of transformation to make it normal. Then you basically do your t-test on the transformed data, okay? Those are the things that you studied in maybe first year or second year in some applied statistics course, okay? It turns out that you could that may be a bit unnecessary now, right? Since in fact the result of a t-test can be almost the same, even if the normality assumptions are violated, actually the calculated computed p-values and the associated confidence intervals, they may not be any different from what you would get if you had done something more exact like a bootstrapping. Okay, so in fact your t-test is actually very robust. Even though even though your data distribution may not be exactly normal, but it usually will work quite well unless the data distribution are very skewed. Okay, which in that case you can use the t-test statistic, but for computation of p-value you would resort to something like bootstrapping. Okay, so so the first thing is to do the transformation, right? So you have data from two groups, right? So basically you do a subtraction of the sample mean, the mean of the group, and you add the grand mean, right? So then basically, that's it, right? So let me just maybe write it down. Okay, so using bootstrapping, to do a two-sample t-test, right? Okay, so right, so first thing is you basically have two populations, right? So this is population 1, population 2, from which you draw a random sample, right? So you draw a random sample, you have x11, x12 until x1n. You draw a random sample, this may give you x21, x22 until x2m, right? Where this subscript here indexes the population, right? This comes from population 2, this comes from population 1. And this is the index within group, right? Within population. So that means the first observation, second observation, and the nth observation, okay? So basically it doesn't matter if your population can be skewed like this one can be something skewed like this. It doesn't really matter, okay? It matters in the standard classical t-test, but it doesn't really matter in bootstrapping, okay, as we will see. So basically you have this, and your bootstrapping algorithm is very simple. Step 1, you resample from, so let me just write this is x1. This is a vector notation, all right? x2, okay. Resample from x1 with replacement, okay. You also do that for x2, right? So you generate a pseudo sample, okay? Pseudo sample for population 1 and pseudo sample for population 2, okay? Then step 2, you compute the t statistic, right? Using the resampled data. So I use I, right? Okay, so you get t of x. Okay, so for example, it will be something like this. If you do a, you could use this form over square root of x1, 1 plus this, right? This is the formula for t statistic with unequal variance, right? You might as well use the unequal variance assumption formula because you don't care about that this t statistic has a t distribution, okay? Because you're going to simulate the null distribution, right? So this form is very easy to compute, okay? So basically, this is your t statistic. So basically, you just plug in the pseudo samples, right? The data from the pseudo samples for x1 and x2 and s1 and s2, right? So that's easy. And then step 3 is basically just you repeat step 1 and 2 10,000 times, right? To generate the bootstrap distribution, okay? Bootstrap distribution for t, right? T is your this statistic, right? Okay, so then after that, how do you make the decision? Okay, so before that, right, this has been forgot about that. So that there's actually a transformation step. So maybe I put it here. There's a transformation step. X1 Xij equals, sorry, Xij transform equals to Xi j subtract X bar I plus the grand mean, right? So basically it means you, for example, you transform 1, 1, right? So it means you take x1, 1, subtract the mean of, just a minute. Okay, sorry, I don't know why it got cut off just now. Okay, let me see. Where was I? Okay, so basically again, so you have the values x11, x12 until x1, and x21, x22 until x2m. So basically you first do a transformation, right? So the transformation will be x1j equals to x1j. Subtract the mean from this group and you add the grand mean, right? This x bar dot dot is you add everything. Okay, you sum I and sum j and divide by n plus m, okay? Right? So your x bar 1 dot is you sum x1j over n, right? X bar 2 dot is you sum your x2j over m, okay? It's just basically the, this is basically just the average, right, of this group, okay? This is the average of both, okay? You do a transformation and then in your bootstrapping step, your test statistic operates on the transform values, okay? S1 square and plus S2. Okay, this operates on the transformed values. All right. Okay, so after that you simulate your bootstrap distribution. Okay, so you have a distribution of t from pseudo samples. So then you will compare against the suppose you look at your t observed, right? This t observed is the t using the original data. Okay, it uses the original data. And suppose you get it somewhere here, right? This is your TOBS. Okay, so your p-value would be whatever the number of bootstrap values, bootstrapped t, that's below TOBS. Okay, more extreme than it, right? Then divide by b. Okay, b is the number of iterations. Okay. So then if you have a two-sided test, you multiply by 2, right? Okay. So it depends on your p-value, whether you want to calculate it on the left side or the right side. It depends on where your TOBS occurs, whether on the negative side or the positive side. Okay. So this is basically the setup, and it's actually very easy to execute. So let's let me go back to the notes again. Okay. So over here, so these are your steps, right? Okay. So basically, you use the transformed data to compute the t statistic. Okay. So then finally, your p-value is given by, this is in a concise form, right? So I write it in using indicator functions. But basically, just now the sketch that I gave you actually explains it. Okay. So this one at so when your TOBS is negative, then you will use this part of the sum, right? find those test statistic values that are less than the TOBS, divide by B and multiply by 2. Okay. On the other hand, if your TOBS is more than 0, then this will be true, right? This will be 1 and that will be 0. Okay. So this indicator function here, it acts like a switch. Okay. Depending on the condition, we use one of them, right? So this is an important way of writing concisely in mathematical statistics, that at an advanced level, generally people will write like this. Okay. In more elementary level, they will not use indicator functions. They will basically just write, if TOBS less than 0, then you'll use this part. If TOBS is more than 0, then you use this part, right? But that way of representing things makes it it's okay, but then it's a little bit not so convenient for doing analysis. Okay. So this is maybe something that you can learn. Okay, then finally, if you want to compute the, so this is a 95% confidence interval, right? So basically, this one involves just basically using the percentile method, right? Just now we talked about that. But here your statistic has to be something that actually estimates the mu1 and mu2. It's not a test statistic, but a statistic that estimates the parameter that you want, right? So basically in this case is x1, the mean of x1 minus mean of x2. Okay. So let me see, do I have an example here? Okay, so I have an example here. So this is an analysis with actually a real example to drive home the message. Right, so this is a question on whether diabetic patients, they are at more risk of getting thrombosis, okay, some kind of blood clots. So this is an early study in the 1980s. And the researcher wanted to use the t-test, right? But they did a check using the QQ plots, the quanta plots, right? So these are the quanta plots. You might have come across that in applied statistics work, right? So this is a graphical method to check for normality. And you can see that if the data is normally distributed, they will actually hug the 45-degree line very closely. So here you see that there's a departure on the right tail for the normal group, and then also slightly on the left tail and the right tail for the diabetic group. Okay. So when you have concerns like this, basically people are a little bit worried about the p-value that comes from this kind of test, right? Because the p-value is only straightforward to interpret if the assumptions of the test are fulfilled. Okay, so in this case it's not fulfilled, so that they are a little bit worried. All right. So how do you use? You can actually use bootstrapping to solve this problem very easily. So here it is. For this one, this is a data set. Later I'll put it into Spectrum. You can play around with it. Okay, thrombosis data. So basically you have the normal and the diabetic group. So you do a t-test. So basically it just basically gives you the p-value is 0.004, right? Very small. And this is your confidence interval, and this is your some estimates of your mean of x and y. Okay. Now here is an execution using bootstrapping. All right. So bootstrapping basically, let me show you. So basically here you have the sample sizes, right? So you extracted the thrombosis data, right? The length of thrombosis, $ normal. The $ extracts the variable. Then this is the grand mean, right? The grand mean is the mean of the two groups of data. And then this is a transformation, right? You do the transformation by, so the data is arranged in 2 columns, right? So you go by column. So apply thrombosis, go by column. 2 means column, right? 1 means by row. So K, so a generic index K. So this K refers to the column here. K minus mean of K plus grand mean, all right? So basically is you do the transformation. And after that, you coerce it to become a data frame, right, for analysis. Okay, so this is some simple processing steps. And then you have your bootstrapping code here. So this part is for your, let me see, the whole thing is here. The bootstrapping. So this part here, because we're going to do two things simultaneously, so it is better to, instead of bootstrapping the observations, right? Because here we want to compute two things. One is we want to compute the p-value from this test. The other is we want to do the percentile bootstrap, right? Where the statistic of interest is the sample mean of 1 minus sample mean of 2. Okay, in this case, the sample mean of normal subtract the sample mean of diabetic. So there are actually two things that we want to compute here, and to do this more efficiently, instead of sampling, so you have to track the data that you actually sample. Okay, so maybe it's better here that you actually resample the labels, right? So here you actually sample the label 1 to n normal, right? And then you go and use those observations that correspond to those labels, okay? So that would make, so you don't have to sample 2 times, okay? You just sample once, whereby you are sampling the indices, okay? And then you extract the necessary data based on those indices. Okay, so for the first thing is here, pseudo sample for the normal group. So I take thrombosis normal, this is ID normal, okay? And then for the diabetic group, I have this one, okay? So this part here, I lift out those that have been transformed, right? And over here, these are the transform as well for the diabetic group, okay? So for p-value computation, my bootstrap t-statistic will be, I just basically, you don't have to put in the formula. You can just execute the t-test, right? Execute the t-test and then extract the statistic, okay? Put a $sign there. So it will basically extract the test statistic from the t-test. For confidence interval, then basically you want to look at the difference of the two statistics, the mean. Okay, the mean of pseudo normal subtract the mean of pseudo diabetic. Okay, and then basically then you return two things. One is your test statistic. The other is the mean difference from the bootstrap iterations. Okay. So once you are done with the bootstrap simulator here, so basically this does the step 1, 2, step 1 and 2, right? So then you iterate, right? Over here is you iterate 10,000 times. Okay, iterate 10,000 times. And since you have got two things here, so I use the transpose, okay? So that the quantity that you want, they are on the columns. Right, so this is TOBS, your observed test statistic. Basically, you just run it. And here is your R output, okay? You're computing p-value from bootstrapping. So this is basically executing from the expression that you saw just now in the lecture notes. All right, so basically you can code this very easily in R. And so the computed p-value is 0.0048, okay? And the percentile bootstrap gives you the 95% confidence interval as minus 33.9 to minus 9.7, okay? So you see that this confidence interval does not cover 0, okay? So you know that you will reject the null hypothesis. But actually, so this is also clearly shown here where the p-value is very small, 0.0048, all right? Now let's compare these two values, these two things with the one that you got from direct application of t-test, right? So direct application of t-test, you got a p-value 0.0039. It's about 0.004, okay? So the one that you got from Bootstrap was about 0.0048. It's just slightly a bit higher, just slightly only, but it's already on the fifth, I don't know, it's like on the fourth decimal place already. And then your 95% confidence interval is also very close, right? Minus 35.4, minus 8.07. This one is minus 33.9, minus 9.7. It's quite close, okay? So basically, whether you use bootstrapping, bootstrap confidence, bootstrap t-test or the traditional t-test, you will end up with the same conclusion, okay, which is to reject the null hypothesis and conclude that on average, right, the mean of what's that? The mean of, there are two things, right? The mean of this let me see, this urinary thromboglobulin is actually, the mean is actually significantly smaller in the normal group compared to the diabetic group, okay? Like the mean of this protein is about 13.5 in normal people, but it is 35 in among the people with diabetes, okay? So this is actually a good marker for risk of thrombosis, okay? So I think this is actually quite established now. So if they will actually measure the this protein in the urine of people with diabetes, okay? So if it is elevated, then they might be put on some kind of medication for preventing blood clots, right? Because if this is too high in the urine, right, so it indicates that this person is at risk of developing blood clots, okay? So this is so the evidence is very strong, right? So regardless of whether you use the t-test with, even though the normality assumptions are not fulfilled, but they are not that different from the more exact bootstrapping method, okay? So it's very nice that the bootstrapping result actually supports the t-test result. All right. And so here in this course, you can actually just recycle this code, right? So basically, you can just recycle the code, and then you basically just need to change the reference to the data set, right? So for another data set, it could be something else, right? Not thrombosis, okay? That will work, right? So the code is not very difficult, okay? Right, okay. So any questions from you so far? Any questions about bootstrapping for hypothesis testing? Okay. Okay, so now I'm going to move on to bootstrapping for estimation of estimation problems, right? Which is on bias correction. Okay, so you notice that in mathematical statistics, you have all these problems about trying to ensure that your estimator is unbiased, right? Okay, because bias actually is undesirable, but sometimes bias estimators could be better than an unbiased estimator. Okay, especially if the unbiased estimator has a large variance, right? So anyway, let's first focus on how to use bootstrapping to correct for bias. Okay. So generally, this method works as follows. Usually, you might actually want to estimate some kind of parameter very directly using just the plug-in estimator. Okay, plug-in estimator simply means that you use the sample version, right? There's no other correction, so that means you don't do any theoretical work, right? You simply just replace the parameters with its sample estimate. Okay, that means, for example, if you want to estimate the coefficient of variation, you would basically just, which is basically sigma over mu, you basically replace it with the sample standard deviation over the sample mean, right? But this kind of plug-in estimators are known to be biased. Okay, that is, if you do the theory, you'll find its expectation, it's almost guaranteed that they will have some bias. Okay. So in bootstrapping, you could correct the bias. You could actually estimate the bias, okay, and then correct it by subtraction from the estimator, right? So the bootstrap estimator for bias is given by the following: expectation of this theta hat star. Theta hat star is the expectation of the bootstrap distribution, which is basically after you get your bootstrap distribution for the parameter estimate using the pseudo samples, you take its mean, right? And then you subtract the observed estimate. Okay, so that will give you the bias, and then you do the correction by subtracting away from theta hat. So that will give you a formula like 2 times of theta hat minus the mean of the bootstrap distribution of the estimator using the sample, pseudo samples. Okay. Now, having said that, right, that if you reduce the bias, usually there is a corresponding increase in the variance. Okay, so this is something called the no free lunch principle. Okay, you manage to drop something, but some other things will degenerate. Okay, so you improve something, but some other things will degenerate. So the thing is, we want to see whether the trade-off is actually meaningful, right? So usually people judge that by using something called the root mean square criterion, which is basically they look at the they look at the square of the bias, and then they add the variance, then they take the square root. Okay, if the estimator that has a smaller root mean square error would be considered superior. All right, because basically when you want to judge the quality of an estimator, you need to consider both its bias and its variance. So I give you an example here. So this example is on the estimation of theta in a uniform distribution, right? So this is a classic example and in mathematical statistics. Okay, so your maximum likelihood estimator for theta is max, right? The maximum of, if you take a random sample from the uniform 0 theta, then of course the largest of these values would be closest to theta, right? So the maximum likelihood estimator is just max of that. And this estimator can be shown to have a bias. Okay, the amount of bias is minus theta over n plus 1, right? Because its expectation is actually not equal to theta, but equal to n theta over n plus 1, right? So of course you could make it into an unbiased estimator by multiplying n plus 1, then divide by n. But here we want to show the technique of using bootstrapping to correct for the bias, okay? So over here, I do a simulation, right? So I create a simulator, okay? So I create a simulator, which is basically, I sample 50 random variables from the uniform 0, 1. So my theta is actually 1 here, yeah? My theta hat is max of x. So I get an estimate of 1, okay, using the max, right? So, and then I nest the bootstrap sample inside, okay? So the pseudo sample will be so I do the bootstrapping here, right? So okay, let me see. Okay, so inside here, there's a function to do the resampling. All right, so I resample. So this is to create the bootstrap distribution of the max, right? So after that, I have I run the I run it 1,000 times, okay, to generate the bootstrap distribution. Okay, so this gives me the bias, right? So the bias, the mean of the bootstrap distribution, subtract the estimate, right? The theta hat. And then I return this, okay? So this completes one cycle of simulation where I actually draw a random sample from a uniform distribution. And then I compute the theta hat, right? And then I try to correct for the bias using theta hat minus bias, right? The bias is estimated from bootstrapping, okay? So after that, I do this simulation many times, right? Because every time you do it, it has a different result. So I want to see what happens if I do it many times. Okay, this is the only way to assess the behavior of an estimator, right? You have to do it many times to look at its different kinds of behavior. So it's simulated 1,000 times. And then over here, so since you have two quantities here, I transpose that, right? So that the quantities that I want, which is the mean of the bootstrap distribution, sorry, the theta hat minus bias and theta hat, they are on the columns, okay? So over here, here I check it, right? So then I check the amount of bias that I got, right? So basically this is the estimate. I subtract 1, okay? So 1 is the known parameter value, right? So this gives me the bias. So this is the bias from the bootstrap bias correction method. And this one comes from the theta hat that is uncorrected, right? Uncorrected for bias. And then here, this part is the variance, all right? You can see that the bias, after you apply bias correction, right? On average, the bias has dropped, right? So it becomes minus 0.008, this compared to minus 0.02, okay? But its variance has also increased slightly, okay? Right? So then to judge this, you have to apply the root mean square criterion, which is you basically square the bias, and then you add the variance, okay? So you do this, you get the following. So here it shows you that the bootstrap bias corrected estimator is actually better than the estimator that's uncorrected. Okay. And over here, this minus 0.02 is actually predicted from theory, right? Your theory predicts a bias of over here minus theta over n plus 1, right? So your theta is 1 here, and your n is 50. So it predicts a bias of minus 1 over 51, which is about 0.02, okay, as predicted. All right. So, okay, so this simulation result shows you how to use bootstrapping for bias correction. Right. So later in the tutorials, you will have some chance to practice on some other bias correction problems using bootstrapping. Okay. All right. Okay. So any questions on the bias correction part? Any questions? So some other examples of bias correction would be, for example, if you have x drawn from maybe say normal mu sigma square, right? So you want to estimate, for example, coefficient of variation, which is equal to sigma over mu, right? So you would estimate this as S over X bar, right? So this is the plug-in estimator. So usually we don't want to, if you are lazy to do mathematical statistics work, that is a reasonable way to begin. And then we know that this is almost sure to be biased. So we want to do bias correction, okay? Right, using bootstrapping. This is much easier to do than to use some asymptotic methods to correct for the bias. So your mathematical statistics need to be quite strong to do that. Okay, so but bootstrapping anyone can do. Okay, once you understand the concept, you know your R basics quite well. Anyone can actually do this bias correction. Okay. So basically what happens is that to do the bias correction, you do the following. Step 1. So of course you already have a sample, right? You have a sample, you say you have certain sample size, right? You have N, you have X bar, you have S, right? So you have, of course you have your data vector, right? X1 until Xn, right? Okay. Step 1 is to, of course, resample as usual, right? That is the hallmark of bootstrapping, right? Resample your data vector to create a pseudo sample. 1, right? Step 2, you would actually compute S over X bar using the pseudo sample. So, right, so I would denote this by 1, okay? And step 3 is just to repeat step 1 and 2, say 10,000 times, right? Okay, so that will generate a distribution of S over X bar. Okay. Right, so from here, then the bias correction works as follows. Okay, once you have that ingredient, so your bias estimate is equal to the mean of the bootstrap distribution of the following, right? Okay, so the estimate is the mean of this, subtract theta hat, right? So your theta hat is, here your theta hat is actually S over X bar, okay? Subtract S over X bar. So this one is using original data. Okay, this original data. All right, so therefore your bias corrected estimator is equal to theta hat minus bias, okay? Which is S over X bar minus this whole thing here. So basically, since you have the same thing here twice, so it's 2 minus the mean of the bootstrap, okay? Bootstrap distribution, all right? So the procedure is actually very easy. In fact, for any parameter, so for example, over here, you want to replace with mu square, square root of mu, whatever, okay, whatever parameter. The easiest way to estimate it is always to use the plug-in. So for example, here, if you use the plug-in, it will be just X bar squared. This one will be just the square root of X bar, right? And they are all biased, so you can correct the bias using bootstrapping by just repeating this procedure, but you just replace this statistics with whatever that you want to estimate, right? The whole procedure is the same except that you just replace the statistic of interest, okay? Right, so this bootstrapping gives a very powerful way of doing bias correction that's purely computational and does not need to involve any knowledge about the distribution of your data, which is very cool because generally all the other theoretical methods, they might actually need this information. Okay, they need to know your data is drawn from, is it a normal distribution or what kind of distribution, right? That can be make the analysis very difficult because depending on what your distribution is, the result will be different. Okay, so bootstrapping actually solves this problem because basically the idea of the bootstrap is that all the information about the distribution of the data is already captured by the empirical distribution, right? So the empirical distribution of the resampled data. So basically, it's like when you do the resampling of your data, right? You are already estimating the empirical distribution. That means the distribution function of this observed data. They actually mimic your data distribution quite well, right? Assuming that your data have been properly collected. Okay, so your bootstrapping will actually work very well if you have done the data collection very well. If you have done the data collection very poorly, right, your bootstrapping will work very poorly. Okay, so this is according to the principle of justice, right? There's also a principle of justice in data analysis. If you give rotten data, right, all these analysis methods, no matter how sophisticated, they will also be rotten. Okay, you won't have a situation where people collect rotten data and then they have some sophisticated theory. Then you put in the rotten data, suddenly you get something golden. It doesn't happen. Okay, so in statistical analysis, the most important is still to ensure that you have a proper experimental design to collect the data and involve randomization, right? So that whatever data you get, right, is representative of the population that you want to analyze. And once you have that scheme, right, even though you don't know anything about the distribution of that population, all these very cool computational methods can be used to solve your problem, your inference problem, okay? So compared to the situation where you actually neglect the collection of the data and then you try to rely on these methods, it doesn't work because your method is only as good as the data that you collected, right? Okay. Okay, so I think yes, it's already almost 4. All right. Okay, so I think we have covered bootstrapping, an important topic, right? Bootstrapping is an important topic that will be examined. Okay, so please take note of that. And it's also easy enough. The algorithm also easy enough to understand and code, right? So I hope you will take note of that. So are there any questions from any of you regarding today's topic?
No.
Okay, so I think if there are no more questions, so I'll end today's lecture. And then just briefly to talk about some other logistics things, all right? Okay, just don't leave yet. Let me see.